So yes, the title, the reason the title is so long because I wanted the title to be very descriptive of the work. So what I'm presenting is based on this paper that we pushed on arXiv back in November, and then it's actually going to be presented again in grades later this week. To conclude, investing in knowledge graphs provides higher accuracy for LLM-powered question answering systems on top of SQL databases. That is a conclusion of this work. So in case you need to leave, now you know what I'm talking about. All right, so what I'll be presenting is how to takeaways that we've had. It's at least 3 times more based on the benchmark that we're presenting if you compare it against SQL accuracy, and it's actually, we're further improving, showing you new techniques that we're doing. And the takeaway from an industry perspective is that if we really want to have AI adoption inside of the enterprise, we must be investing in knowledge graphs. We really must be investing in treating metadata and semantics as a first-class citizen, which is something that I think little by little is starting to happen, but we need to do that more. I think part of the work that we're doing here too is showing that we need to have more bridges between industry and academia. And everything that I've presented here has been just me reaching out to a lot of folks in the industry and academia and getting feedback. So that's truly, I think, like the scientific process of like science is a social process. So when we started out this research, just to kind of put things in perspective on timing, over a year ago, almost a year and a half ago, when all the LLMs and GPT starts out, people start saying, well, now we can do natural language to SQL. It's going to be great. It's going to be easy to go do. And we start seeing all this test that people are doing. And of course, it's just kind of play examples, small tests over small schemas of things. And it was really not well understood is to what extent can these large language models accurately answer enterprise questions over enterprise SQL databases? That's what I want to understand. And then we kind of intuitively, we knew like, oh, we need to have semantics. We need to have this context. We need to have knowledge graphs, and it should improve. But what we don't know is to what extent that knowledge graph is actually going to improve. What is the extent that it's going to improve? So these are the 2 research questions that we started off with. Actually, last week I was at the Snowflake Summit, and a year ago at Snowflake, people were just starting to talk to LLMs, and I'm having a bunch of conversations with the Snowflake product managers, and they were the ones who actually posed this challenge to us. They said, okay, Juan, we get that you talk about semantics and knowledge graphs all the time, but how much better is it? So they actually challenged us to go do this benchmark. They're actually one of the inspirations of why we did this. So the hypothesis here is, if I have an enterprise relational database, and I have a knowledge graph representation of that, I've invested in the semantics to create that knowledge graph representation of my enterprise SQL database. And I take a question and I pose it directly over the SQL database, and I compare that over a question over the knowledge graph representation. The expectation is that the accuracy is going to be higher. So that's what I'm expecting the results to look like. And what I want to be able to make a claim like this and say, hey, invested in knowledge graphs provide higher accuracy. I want to be able to have evidence that supports this claim. So we want to have a benchmark around this. Now, first of all, text to SQL is a very old problem. I would argue that having conversations with your data is one of the inspirations for computer science. And the problem of text to SQL itself has been probably 30 plus years. And I think the popular benchmark in this area is Spider. It's a kind of the de facto benchmark that a lot of people use. Now, the thing that if you look at things like Spider, all these benchmarks out there, is that they're academic. They are small schemas around there, so they don't represent what we're seeing in the enterprise world. So we first wanted to look is for some enterprise SQL schemas around that. So OMG, the Object Management Group, is a standards organization that actually has an insurance model on property and casualty. And it's an enterprise data model that was built probably 10 plus years ago by multiple experts. This represents what an enterprise schema looks like for insurance, and actually insurance companies use this as a starting point. So that's number 1. Number 2 is on the types of questions that we want to be able to go ask. So again, if you look at the benchmarks that people have, the academic benchmarks, they're a laundry list of questions. Why do those questions exist? So we really want to be able to have questions. I'll talk about this kind of a different spectrum of complexity. And third is we want to make this context, the semantics layer, explicit. The existing benchmarks don't talk about the semantics. And the whole point here, remember, the claim I want to make is that by investing in semantics, by having this work, the accuracy is going to improve. So again, this is just a screenshot of the enterprise data model. You can go find this right now. It's open, download the SQL DDL around this. So this is a real enterprise SQL schema that comes through this. Now, when it comes to the questions, there's two spectrums that we look at. One, we call it the schema complexity and then the question complexity. So the schema complexity is, I just have a couple of tables. I do higher schema complexity, I need more than a couple of tables, right? So I think the cross is like 4 tables is what we looked at. And then when it comes to question complexity is this just a list of things? Or am I starting to talk about metrics, about key performance indicators that are going to involve some aggregation? So if I say so you have this quadrant now, right? Basically easy questions on easy schemas. Hey, return me all the claims we have by claim number, open date, and close date. I just need probably one table and project 3 columns over that. I increase the complexity of the question, but still kind of keep it on a small amount of schemas. What is the average time to close a claim? I need to aggregate it. Probably need to do a little subtraction around this. High schema complexity and low question complexity, I'm still projecting a bunch of values, but I need to join a bunch of tables together. And then this is kind of the big goal here is to be able to have complex questions over all these complex schemas. What is the total loss for each policy, where total loss is defined as this and the. By the way, these questions are the questions that any insurance company are going to be asking day to day, like total loss is something, loss ratio. These are the metrics that they talk about every day. And something that I want people to take away, and I tell this to all kind of industry folks, is that when you're thinking about testing and creating these systems, put the questions that you want in this quadrant. So this is a framework for you to take away to figure out what am I going to try to go do, what am I trying to achieve, and start building towards that. So just quickly, because instead of time, all this is very explicit on the table, on the paper, and we have everything is public, and we have a GitHub repo. So again, low schema, the easy, right? So if that's my particular instance in my data, I'm expecting this answer. So the benchmark has question-answer pairs. The question in English and the expected answer given a particular database instance. It does not include the actual query. Really, you don't care about the query. You care about getting the right answer. Because systems that eventually you want to go evaluate this is not a system that just generates a query. It's probably going to be an agent-based system going back and forth and so on. What is the average time to settle a claim by policy? Again, you can see, we joined 4 tables. We needed to have a subtraction between dates to be able to do an average over. Low question. So for example, I need to be able to get the loss reserve, the expense statement, and so forth. This is how the database is modeled. You have one table about amounts, and you basically have different tables that define the types around that stuff. So you need to join these things multiple times to do that. That's how this stuff is actually modeled. And now we get to combine a bunch of tables in here, right? Then finally, when we get to the context layer, we want to be very explicit about what the stuff means, right? So which means that I want to have an ontology, right? This is separated from the physical schema, and then be able to have the mappings, the transforms from the source to the target. In this benchmark we present, we're using open standards around this stuff. And of course, as open standards, we have RDF and OWL and Sparkle to go this, R2RML to represent the mappings. And as I'll show you later, we have other people already replicating this stuff independently. And actually, Jesus from Neo4j has been doing a lot of this work too. He's had even a lot of webinars and stuff presenting this. So an example of a mapping that can be really simple is that you say, what is the concept of a claim mean? Oh, there happens to be a table called claim. So the claim, every row in the claim table represents an instance of claim. And then the column company claim number is mapped to claim number, and claim close date maps to close date, and so forth. You can have very simple one-to-one mappings, but then you may have mappings that involve joins, that involve values. So how do I know if somebody's a policy holder? Is because in the data there's a value that's called pH. You can guess these LLMs don't know that. They're always going to get those things right. Or, sorry, always going to get those things wrong. But if you invest in doing that, you make that explicit. So the setup that we did for the benchmark and the results that we're showing you, on purpose, everything is extremely simple, naive, and you can even argue it's kind of stupid. But that's the whole point, because we want to have a baseline. So we have a very simple zero-shot prompt that we're testing. And what we're doing for the graph, from the knowledge graph side, is that we're using the mappings to create a virtualized knowledge graph in this case. And then the Sparkle query is generated, which gets translated to SQL. This is completely deterministic. This could be replaced by a RDF graph database. This could be replaced by any other Neo4j database, whatever, but that's just the setup that we have here. And explicitly, these are the very simple prompts that we tried. The following is a SQL DDL. Paste it in. Write a SQL query for the following question. Following is an OWL ontology and internal syntax. Paste that in. Write the Sparkle query for the following question. Those are the prompts that we're using. So the results I'll be showing you are based on those prompts. Again, the point is we're doing something very, very simple to understand that baseline. So how are we scoring? What does accurate mean? So of course we're using the notion of execution accuracy that comes from the spider benchmark. It's basically saying it's a binary. It's right or it's wrong. It does not take into account the column orders or the labels. So for example, if I have this particular question and this is the expected answer, and I run this through one of the prompts and I get this particular answer back, you can see that the labels are different, the orders of the columns are different, even the rows are different, but that's an accurate execution. In this case, we have everything here is the same except for claim numbers are different. The answer itself completely is inaccurate. This is just the way how things are defined, using that same definition of accuracy that comes from the spider benchmark. Now, LLMs, we know, are non-deterministic machines. So if I ask a question once and I get a query back, if I ask the question again, not necessarily I'm going to get the same thing back. So what we're doing is that we're running the question over and over again, and then we have this notion of an overall execution accuracy, which is the number of times I got it right over the number of times that I executed the query. And finally, I can have an average overall execution because I want to be able to group a set of results by questions. Let it be for all the questions and then also by quadrant that I have. So that's the average overall execution accuracy. So the results. This is where that 3x comes from. So by running, oh, I forgot, in the benchmark, in those 4 quadrants, we have around 10 questions each, right? And all these questions end up building to what is the loss ratio metric. The loss ratio metric is total loss. So basically all the questions that we're doing are building towards that. So from here, we start seeing, this is where that 3 times more comes in already. This is already pretty fascinating because, and I will say this was all GPT-4, right? Because this is implying that just by investing in doing the semantics, and GPT-4 understands OWL and Sparkle. That I was very skeptical. I didn't even think it was going to work just because I didn't even think it was going to know that. Now here we have a heat map, right? Because the devil's in the details. So 100% is that if I ran the question 100 times I returned the right thing, right? So 30%, whatever. So here's kind of a different heat map. Why is this happening? God knows. We don't know what's happening inside of LLMs. So this opens up a bunch of questions of why. Now, what's interesting is to go see what happens per quadrant. So not surprising, right? And the schema is less complex. These things are going to be easier. We'll have higher accuracy. The moment that the schema gets more complex, this actually goes to 0. Now, we'll see that a lot of the questions that this happens is because it requires a knowledge of knowing some of the values that it doesn't have, right? So you may say, well, that's kind of cheating around. It's like, no, I said from the beginning, I'm investing in the semantics. I'm investing to figure that out and make that explicit. Now, I can tell you that in since last year, a lot of the vendors, Snowflake, Databricks and stuff, they were acknowledging that if they're creating these co-pilots, they were only going to allow up to 4 or 5 tables. I'm like, that matched the results that we have. And actually, these systems right now that are being created are only allowing 1 table. You can sit down there. Funny. That's fine. So they're only allowing 1 table for this because they're reducing the problem. They saw that problem is so hard that they're reducing it just to 1 table. Again, you can see the heat map in this case. Now, which is really, really cool, and what I find fascinating how this industry is really interested to kind of move forward, is that we published this work, and then we started seeing other companies independently, and actually not graph companies, just companies who are talking about semantic layers, saying, oh, that is actually, yes, that makes sense. And we want to go prove it works with our product. I'm like, I know it's going to work with your product. Well, this is science, right? The theory says it's to do experiments and you go do it. And it was just fascinating to see other vendors replicating the work completely independently. I mean, DBT, for example, I woke up one morning and my phone is buzzing. Everybody's telling me it's like they published the whole thing. And they replicated it in so many different other vendors. So when we published this back in November, every big tech company, all the different database vendors, they acknowledged it. And actually many people were saying, finally, this is evidence that I can say, we've been talking about semantics and knowledge graphs. Now I can actually share this with other people. They're like, you got to pay attention to this. So what's interesting is to understand why things aren't working, right? Okay, we've got the positive result, what's happening in the negative result. One of them is what we call partial accuracy. Basically, is I almost got it right. You should give me some partial credit. So this happens a lot. I got the wrong identifier back, but a lot of the body of the query is over there, or you forgot to return a column or something. So it's like, and in practice, this is when these systems get more practical. If you give this to a user could say, hey, you forgot to give me this, give it back to me, right? So these partial accuracy results should be able to kind of increase the accuracy in a way, or we should have some metric for partial accuracy. But what's really interesting is inaccurate results. Now, of course, you can mention this is the hallucinations, right? When the generated SQL query came up with a column name that doesn't exist. It generated values that don't exist. It generates joins that may even work, but they're the wrong joins to be done. But when it comes to the Sparkle, to the graph, it was generating the incorrect paths. So basically it said it went from A to C when it should have been from A to B and B to C, or it got the direction wrong. That's what most of the issues that we saw. So just simple examples here. So that's the actual question. These are the generated queries based on that prompt that I showed you. That's not the value. Policy holder didn't know what the code is. This is partially correct. In return, you see the identifier, the IRI for policy, instead of the actual policy number. In this case, we have, that was a column that was hallucinated. That column name doesn't exist. Here, it's interesting. I'm asking for policy holders, but it is not being returned in the select clause, but it had it here, right? So the body of the query was correct, but the head of the query was missing some stuff. This was partially correct, right? The claim identifier is not the claim number. There's another column for that. That was correct. Here again, that's a hallucinated value. That was correct. This is a really cool. You give this complex question with that ontology. I mean, all these joins are wrong. That's correct. It's fascinating, these machines. It's really, really fascinating. It does this. So we started with this question, right? We have an answer. So using GPT-4 and that zero-shot prompt, we see this improvement of 3 times, and then we see how this improvement goes on each of the different quadrants. Now, we started out with this hypothesis, and I feel now very comfortable making this claim that I have evidence. And we see other organizations independently replicating this work. So I think this is something that is now kind of well understood. Again, I was at Snowflake last week, and now Snowflake is launching some semantic layer thing, and everybody's doing this. Everybody's starting to invest in semantics. So this is something that is now happening. And I'm probably take a little bit of credit here because people have been following the work that we've been doing around this. But there's one more thing. So this is the work that we presented in November, but we really got like, okay, people want more accuracy, right? Everybody's saying, well, it needs to be 100%. I'm like, hold on, you don't even know what 100% is, right? You get reports every day. Like, how do you even know that that was correct? But obviously, we want to be able to increase and understand that. So here is the observation that we have around these paths. So when we talk about insurance, I mean, insurance it's not an interesting thing, but there's nuances around this. So you say, for example, I pay a premium, I pay something for the policy that I have. But in reality, how things are modeled is that you have a policy and you have a set of coverages. So I have an insurance policy and I have a coverage for my house, for my car, right? And then if I pay a premium for each of these things. So there's like that coverage in the middle. And what we saw a lot is that you see here, policy goes directly to premium when it actually should go to that middle thing. So what we observed is that, wait, you're generating a query and I actually know the semantics. deterministically check if that was right or wrong. So let's say if I model things, a policy is sold by an agent. What does this mean? That if I have that property sold by, the domain is policy and the range is agent, right? So if I ask this question, return all the policies that an agent sold, and I get this query back, what happens? This is incorrect. I know this is incorrect because sold by, the domain is policy, and then here it's saying the domain is agent, and assuming the policy agents are different, I'm like, oh, this is incorrect. So what happened is that we started looking at all these different types of errors and we found all these rules, and we said, we can now use ontologies to actually deterministically check when the queries were incorrect generated from the LLM, and then check them, so if it's right, if it's wrong, and then actually repair them. So that was this latest work that we presented a couple of weeks ago. We just pushed it on archive. So just to kind of wrap up here quick, the question now is, to what extent can I use this ontology technique to further increase the accuracy to go do that? And then it actually is, because this is a deterministic check, I have a bunch of rules, which are those rules that fire the most? And actually can give me some sort of insight of like what's happening inside the LLM. So again, the hypothesis is that I can further increase the accuracy. So this was the actual setup that we had before. And what we've done now is that we have this this ontology-based query checker, which has a set of rules. And it can check if it's yes or no, if it passes or not. If it passes, it sends a query. If it doesn't, I can create an explanation of why I got it wrong, what was the incorrect query, and then we actually can repair it. And the repair is using the LLM itself. And then if it repairs it, it puts it back here. And we just do this a couple of times. We actually test this 3 times. And if it says, after 3 times says no, I return an unknown result. So I'm not going to go into too many details here just for the sake of time, but we actually just by observing the logs of what's getting wrong, these are the types of rules that we use. And they're actually rules over the body of the query and then rules over the head of the query that we can go check to go see it. And so for example, right, I have, if a policy is sold by an agent, right, the other one, and I get this query, this would be wrong. And what we do is that we can actually implement these rules in the query itself, in Sparkle in this case, right? Yes, I could use shackle or other things, but we just did this here. Very simple to go do. So we have a bunch of these rules that we implemented them. And then the LLM repair, what it does, this is literally the prompt. So when we run this previous query, if this query returns an empty result, we know it was correct. If it returns a result, we know that those are the errors. And then we turn those errors into this. We have this query with some issues outlined here. Those issues are basically every single tuple of the query of that rule. Please rewrite it. That's it. Super simple. This high complexity, look at that, how it improved. Just by doing that simple, again, this is super simple, nothing else. And what's interesting is here is that we try to improve things after multiple times it did it, and so we have this unknown repairs. So basically, if I look at the error rate, which is the times that it got it completely wrong, because unknown is not an incorrect answer. For even the simplest questions, we're now at an error rate of only 10%. We're getting really close to something that's actually usable, which actually we now have this implement. And when we look at what are the types of rules that are generated, we see that 70% of the rules that were executed were rules over the body of the queries. And the majority of the rules were things that revolve with the domain. A hypothesis that because this thing writes from left to right and the domains are on the left side, that's why if it gets it wrong earlier at the left side, which is the domain. So if we put this all together now, overall, we see how we're increasing, and this is the 8% that we get from the unknowns. Now this is starting to increase. We're getting more and more with this. So that accuracy, if we just start without any semantics knowledge graph, 16%. We use the knowledge graph with that simple prompt, 54%. And now if we use the ontology to do some check afterwards, 72%. And the error rate, we've been decreasing it. And as we have this implemented right now in our system, in our own product, which I will tell you what we're doing is actually, this is why it's super cool right now. We're building autonomous agent systems. Everything I just said is just one part of this question answering system that we're doing. We're building state machines that is traversing all that stuff. These techniques that I presented here are just states in that state machine that we're doing. So this is what I think is really, really exciting right now when it comes to all the AI stuff. So to conclude, reasons why you could cite our work. Yeah, by increasing by investing in knowledge graph, you have that accuracy at least 4 times more. Knowledge graph, this is evidence that you need knowledge graphs, need semantics for AI. Ontologies can really make an impact in here. This is another thing of why you should start investing more in ontologies and have that curated, have that governed. And I don't know is a perfectly valid answer, which by doing that reduces the error rate too. Thank you very much.